All right, so hello everyone. Thank you for coming. Very glad to have a full room today. So I'm going to talk about face processing and computer vision. So my name is Gabriel Bianconi. Just quickly, a little bit about my background. I'm the founder of Scalar Research, which is a machine learning consulting firm based in New York. And before doing this, I spent a couple of years at the Stanford AI lab doing research on computer vision, particularly applied towards healthcare and ICUs and hospitals and so on. So I want to cover today basically two main areas of face processing. So first I'm going to talk about the theory behind face processing and some of the computer vision principles that people applied to tackle those problems. So I'm going to talk primarily about detection and recognition, which are the two main tasks, but then briefly touch upon a couple other tasks that people are researching in this area. And the idea here is that I want to give some intuition behind why people are applying the techniques they use in face processing and what are some of the main challenges that people need to solve in order to have something meaningful here. And then I'm going to shift the focus towards the more practical sides of things. I'm splitting this into the prototyping side first. So if you want to create a face processing product, how can you create a quick prototype, how you can quickly iterate using on those technologies, and then once you've found something that's meaningful and you want to scale, how can you take those techniques and take something that works at scale for a large variety of users and so on. So I think it's important to separate the practices into those two fields. So like I mentioned, first I'm going to talk about the theoretical side of things. Start with facial detection. The main importance of face detection is that the vast majority of the other face processing tasks are going to depend on a good face detection algorithm to work. So if you want to do, let's say, facial recognition, you first have to detect the faces in the pictures to then apply the facial recognition algorithms. And if your face detector is not working properly, it doesn't have a good boundary on the faces, or doesn't detect all the faces and so on, you're not going to be able to get any good results for the downstream tasks like recognition and so on. So that's why it's a very essential task that touches upon basically every other face processing task. I want to talk a little bit about the history of how people are tackling face detection. So this all primarily started in 2001 with something called the HAR-like features. Basically, the idea here is that people created manual features in computer vision. This is before deep learning or anything like that. They had to manually specify how to extract information about the faces and then use that to try to create a heuristic or algorithm to figure out where faces could be in the picture. So these two researchers, Viola and Jones in 2001, used this to create the first real-time facial detection algorithm. The idea here is that using the squares you're seeing here, those are basically kernels, which are basically feature extractors that you can apply to images. So for example, the vertical ones, this is when you're looking at the pixels of the image, it's looking for this pattern on the pictures you're looking at. So this is looking for vertical edges, horizontal edges, texture. So you apply a couple of those kernels. You apply this throughout your picture. So you're basically sliding this across the picture, and all across your picture, you're looking for those patterns. And based on those, you're going to try to make a prediction. So if you see, okay, in this region you have a lot of vertical lines, in this region you have about horizontal lines, here you have textures and so on. If you combine all this information you extracted and then apply some sort of traditional machine learning model, then you can make a prediction for what's there. This was a pretty coarse way of determining what's being represented in the picture, but the main idea here is that once you look at a picture, you're looking at millions of pixels. So for example, your iPhone X pictures, you're going to have about 36 million parameters from the pixels they have. So you can't have that all in your machine learning model. So using this and trying to figure out look for those patterns like lines and textures and so on, you can summarize your picture into something that's important and then try to make a prediction based on that. And then this evolves a couple years later to something called the histogram of oriented gradients. This is still a traditional computer vision technique in which people are using manually determined features to try to summarize a picture. So the idea here is that you want to look at the gradients from the colors and the directions of those gradients and their intensities to try to summarize the pictures. So here's an example. If you look at the picture of the face on the top left, you're basically going to splice that up into several small cells. So basically, you're going to create a grid on top of this picture and split that up into small cells. And for each of those cells, you're going to compute the gradients of the color. So for example, you have a lot of vertical lines or lines in all sorts of directions. How are those colors distributed? then you're basically going to summarize those and into a histogram. So this is basically saying, okay, we have these many gradients vertically, this many horizontally, in all sorts of directions. And as you summarize the picture throughout this, you get a lot of information about the textures, the shapes, and the colors, and so on. And then you're going to use this to make your prediction. So in practice, if we compute the gradients from the face, we get the picture on the left. So basically, we split that up into several small cells. And for each of those cells, we're basically aggregating the gradients from the colors and so on. And then if we do that throughout, let's say, thousands or hundreds of thousands of faces and average them out, then we get the picture on the right. This is the abstract representation of what a face looks like in terms of its gradients. And then once we want to do a prediction using the system, we basically compare your picture and its gradients to the one on the right. And if there's a match above a certain threshold, then we can determine with some sort of confidence that there is a face in that position. And the idea here, too, is that let's say you have a picture that's not only a picture of a face, you have, let's say, a whole scenery or something like this. We can take this image on the right and basically scale it to different dimensions, so small faces, big faces, and so on, and slide that across your picture. So as you slide that across and you see a match, you're basically going to get, okay, there's like 90% chance there's a face, there's like 30% chance, and you can take the best candidates for you to detect the faces there. And the main limitation here is that, as you see here, this is only a frontal face and a pretty standard face. So as you start to look for more challenging faces in different angles or faces that are partially occluded, this match is not going to work very well. So this was the main limitation of the system. It worked very well for like the standard face, like a frontal face and so on, but it didn't generalize too well. So the main advance here happened when people started introducing deep learning towards face detection. So this started with something called the OurCNN. This was the first time when people used neural networks, or in this case, a convolutional neural network for object detection and then face detection. The idea here is that they wanted to use a convolutional neural network to do those feature extractions. So before deep learning, you had to manually specify how to extract features from your images. So either using those gradients or using those initial kernels I showed you. But the main advantage of deep learning is that giving it enough data, you can have the model learn how to manually take the feature. So you're feeding the images to the model, and the model can spit out something meaningful from it. And by doing this, then, we had a breakthrough in performance, in particular for those cases where I mentioned, okay, it's not just a frontal face, standard face. So here the model, if it looks at enough faces from different angles, different lighting conditions, and so on, it can learn to identify those two. So the idea is that for the OurCNN, the CNN was used to extract those features. And in practice, it looks kind of like this. The advantage of deep learning is that it's a hierarchical model, so it learns more and more abstract information about your data. So it starts on the top left. So the first layer of your neural network is going to learn some pretty granular information about the image. So this is going to be strokes or changes in color or things like that, very low-level information about the image. Then the next layers are going to start combining that information on the bottom left, and you're going to have more meaningful representation about strokes and curves and other low-level shapes like that. This starts to get combined into more and more shapes and more abstract information until you start seeing information, for example, about facial features, and eventually you can combine those as well to have information about the complete faces on the bottom right. So the idea is that the CNN can start with the image itself and learn how to extract features that goes all the way to the very abstract information that you need to make those predictions for face detection and so on. And at the high level, how this OurCNN system works is that you start the image on the left. You're going to use some sort of algorithm that suggests regions of interest. These are regions that the algorithm thinks are very likely to have a face or some sort of object you're looking for. So in a lot of cases, you're looking for, let's say, 2,000 regions of interest in an image. So this is if you have any chance of having an object there, you're going to make that as a proposal for you. Then for each of those, you're going to basically crop that out of the picture, reshape it, and apply your CNN to it. And then the CNN is going to try to determine if that region you had as a proposal was a face or something else you're looking for. and then you're going to use the information from the CNN, those features is extracted, to try to make a prediction for whether it's a face or not, and also the exact bounding box for that object. So in this case, for the OurCNN, the CNN is only extracting the features, and then you're using a different machine learning model, let's say an SVM and so on, to actually determine the other properties, like the class, like person or not, and also the bounding box. This was very interesting in the terms that it managed to get very high performance, but it was also very slow. So to make a single prediction of a system like this, it took around 1 minute for it to run on a single image. So then a couple years later, people came up with this new idea called the fast OurCNN, which was an improvement to the OurCNN that didn't only use the convolutional neural network to extract the features, but also to make the predictions for whether it was a face or not, or different classes as well, and also determine the bounding boxes. So before we were using a separate model for this, but now the convolutional neural network starts with the region proposals and finishes with the final predictions that you have. And by doing this, the predictions are actually 200 times faster, and in some cases it was in the range of 1 or 2 seconds for whatever image you're working with. And also, again, in this case, it's still not something that you can do in real time, but it's substantially faster than what we were getting before. So the idea here is pretty similar to what we were doing before, but we basically merged the last 3 steps into a single neural network. The idea is that we start with the image, create a couple region proposals, and then for each of those proposals, we're going to apply this convolutional neural network, extract the features, and the network itself is also going to predict what the probability of having different objects and so on, and also where the bounding box should be for that. And then finally, we had a third iteration of the same technique called the faster OurCNN. People weren't too creative with the names. These are actually how the papers were called at the time. In this case, the main advantage here is that before we had those region proposals from a separate algorithm, but again, they merged this into the neural network itself, and the neural network could make those region proposals. So now finally, you could feed a raw image into the network. The network would generate some proposals internally for where objects likely are, then examine it in each of those, and then finally make a prediction for what's there and where the bounding box should be. And this was now 10 times faster than the previous iteration, and finally we had the first real-time technique for face detection using deep learning. So this is now able to make a prediction in around 200 milliseconds. So again, just to summarize what's going on here, it's now merging all the steps into a single neural network. You start with the image, it creates the regions proposals, and then using the same information from the convolutional neural network, it's able to make the predictions for whether there's a face there or not, and also whether where the bounding box should be in that image. So this is how people finally got a robust, fully deep learning system for face detection. And since then, this was in around 2016, and since then people have iterated on this technique for things that are specific for face processing that improves the performance, but overall the high-level ideas are similar to this. So one of the advances people did was called the MTCNN, which stands for multitask CNN. The idea here is that if they could optimize for 2 face processing tasks at the same time, they would achieve better performance, because then the model is focused primarily on the information that's relevant for the faces. So here they're not only detecting the faces, but they're trying to align the face. So that means basically determining the angle of the face, so that in addition to determining where the face is in the picture, you can also rotate that so that when you're doing facial recognition or something else with that image, then you also have a more standardized or normalized version of the face. And the idea here is that, similar to the previous system, you start with the face, but now they're going to resize this face to several dimensions so they can look for different sizes of faces. And then they're going to start with a bunch of region proposals. They're going to filter that out in basically 3 steps. So we have 3 neural networks here. One that makes very coarse, very quick predictions. And then the second one is going to take those predictions and again filter them out and refine the ones that remain. And then the final one that makes a final 1 or 2 or so predictions for where the faces might be, and also aligns the face. And here, when they're doing the alignment, they're basically trying to determine where the mouth, the nose, and the eyes are, and based on that, try to determine the angle of the face. So this is a 2D alignment of the face. And then finally, we get to the current state-of-the-art model, which is called DSFD, which is dual-shot face detection. which draws heavily from what people are doing in those cases. And if you're familiar with general computer vision, it takes some principles from single-shot detection. And the idea here is similar to this idea of refining the predictions from your proposals. It's a two-level neural network, as they call it. It starts with the image, feeds that through a convolutional neural network that makes an initial set of predictions, and then it takes those initial features and the initial predictions and makes a second pass through the image to refine those predictions and refine the features to make a final prediction for you. And by doing this, they're able to achieve the current state-of-the-art result. This was a paper that was published at the end of last year. And in terms of the performance of where we are, the main benchmark for face detection is the wider data set. It's split into three classes of difficulty for the images. And we can see that even in the hard ones, we achieve over 90% performance. And those are images where even a person would have a hard time trying to figure out where all the faces are. You can see, for example, we have faces inside cars where there's a lot of reflection and darkness and so on. So it's a pretty challenging task even for a person. And now we have convolutional neural networks that are able to achieve very good results here. So like I mentioned, this is the first level of prediction that you have to make for any of the tasks you want to do. But people are primarily concerned with facial recognition in a task like this. So once you have detected the faces, you have the crops of all those faces, the second thing you want to do is actually recognize who is being pictured in all those crops. So this is where facial recognition comes in. When people are talking about facial recognition, they're usually talking about a group of several different tasks that actually change a lot how you're going to tackle the problem. So first you have verification, which basically means given two faces, can you say whether they're the same person or not? Then you have identification. You're giving a single picture and say, who is this person? It can be from a large set, from let's say thousands or even millions of people. You have to determine who that person is. Then you have grouping, which is basically, okay, here's thousands of pictures of faces. Can you group the faces of the same people, even though you don't know how many people are there and who those people are? You're just basically trying to cluster those faces into the same identity. And also for all those problems that we're working here, we have two main variations for that. The first one is called closed set recognition. This basically means that when your model is training, you have access to all the identities that you can potentially see in the future. So you know all the people that you might want to recognize. So let's say you're creating a recognizer for celebrities. During training, you might know already all the celebrities you might want to recognize with that model. But you also have the open set variation in which you don't know all the people that might come up, and your model has to be able to infer about people it hasn't seen before during training and so on. So this is the example, for example, let's say you're Facebook, you can't train your model on all your current and potentially future users. So you have to learn a model right now that can generalize to new people it hasn't seen during training. So you have to train on, let's say, 1 million users and then apply the same model to 1 billion users and have it still work. And with all those different tasks and different variations of the tasks, we're going to apply different sorts of techniques on how to handle them. So when we start with closed set recognition, closed set, like I mentioned, you know during training all the people who might come up later in the future, so there's never new people coming up. If you have new people, you have to basically retrain your model. And the example, like I mentioned, would be, for example, recognizing celebrities. In this case, it's going to be structured basically as a classification problem, and each identity or each person is going to be one of those classes. And one of the challenges here is that a lot of classification problems, you have, let's say, 100 classes or 1,000 classes, but here you could potentially have up to 1 million classes or sometimes even more. So this becomes one of the main challenges for the system. How can you have something that meaningfully can classify into, let's say, millions of classes? When you're working on a closed set system, for identification, the idea is that during training, you're going to create one of the classes for each of the people you have. And then during testing, you're going to feed a new picture, and the model is going to assign a probability for each of those classes that you have. And then you're likely going to take the one of the highest probability. When you're doing verification, though, it is pretty similar still. You're going to feed the two images. You want to know whether they're the same person or not. And the model can do either of two things. First, it can spit out the probability of them being the same person or not, and that's it. Or it can spit out basically the probability of them being each of those millions of people you have in your classes, and then you can compare those millions of probabilities and then determine the overall probability. So you can train the model in two ways. Either have it give you the final prediction or give you the intermediate step, and then you compute that yourself explicitly. Then we shift to open set recognition. In this case, like I mentioned, we can have new people come up during training, so you can't have classification. So if you're going to do classification, you know beforehand all the classes or all the identities you have. But here, if you have new people, you can't have the model simply assign them to this class. So this is going to be what's called a metric learning problem. It's not assigning each of the samples to a class, but instead it's going to create what's called an embedding. An embedding is basically when you map each of those samples, in this case, each of those faces, to a vector in a coordinate system. So basically, you take whatever sample it is, and it's going to give you a vector at this point. It's usually a very high-dimensional coordinate system, so let's say 300 dimensions or 1,000 dimensions and so on. And people do this for all sorts of data. You can do this for text, you can do this for graphs, but you can also do this for faces. And then the idea is that when you generate those embeddings, you want to have them such that if the embeddings are similar, that means that the original samples were similar. And if the embeddings are not similar, then the original samples weren't similar. So in this way, even if you haven't seen the person before, you can generate the embedding for two pictures of that person, and then those embeddings are going to be very similar to each other, so you can compare the distance between those embeddings. And when I'm talking about similar here, it can mean several different things. You could train the model to have it similar be the identities of the people. It could be a physical characteristic. It could be something like gender and so on. Or we could have even things about the properties about something that you want. Let's say the person is smiling, the person has a certain hair color, or things like that. But the interesting idea here, if we train this on a very large data set for a general task like recognizing the same identity, then the model itself learns to input a lot of those information about physical characteristics and so on into the embeddings. So even though it's not explicit in the vector what gender and so on it might be, you start seeing that a lot of, let's say, men are going to be closer together in that embedding, a lot of women are going to be closer together, a lot of people are going to be closer by age and so on. So those embeddings are going to start absorbing a lot of that information, which then the model is using internally to represent the different identities. So this is one of the main advantages here, is that you're not only learning how to do recognition, but you're learning how to extract a lot of information about the people. So then, now that we know how those embeddings work, the idea for doing identification is pretty similar to classification before, but instead we're generating the embeddings and then computing the distance between known embeddings that we have. So in the case of identification, we're generating the embedding for all the people you want to compare against and also the new test sample that you have, and then you're going to take the closest one as the prediction that you have. So for example, let's say you're Facebook here, you could generate the embeddings for all your Facebook friends, and whenever you upload a new picture, it computes the embedding for the new faces and compares against the known embeddings for all your Facebook friends, and then takes the closest one to make the prediction. Okay, this is likely going to be your friend, whatever, let me make this suggestion for you. When you're working with verification then, the idea is pretty similar. Your model is going to output two embeddings, one for each of the faces. You can then compare those embeddings against some sort of threshold, and then this is going to give you some distance, and if it's below a certain threshold, you can say this is going to be the same person or not, based on whatever threshold you want to set. And just to give you some intuition of what's happening in classification versus learning those embeddings or those metrics, when you're doing classification, you basically want to draw a boundary between what all those people are being represented. But when you're learning those metrics, you want to basically have some empty space to account for the new faces you want to have in the future. So you basically want to have all the points being condensed as much as you can, so that if you have a new person, ideally that person is going to be mapped to a different point in this sphere, for example, where it's far from everyone else you've seen before, but then ideally all the photos from this person are going to be mapped together as well. So this is how it's able to generalize compared to the sphere on the left to faces that you haven't seen before, and ideally not confuse your new samples with the old samples you've seen before as well. And in terms of the performance we're actually getting very high performance already on standard facial recognition. So again, the benchmark for this is usually the LFW dataset, which is the pictures of like a number of people in several lighting conditions, several angles, and so on. And they're able to get close to 100% performance. This is above what a human would be able to get in a task like this. So in terms of like a standard facial recognition system, it's pretty much a solved problem. But now we have a lot of research into tackling the edge cases of those recognition problems. So one of those is called the cross-factor recognition problem. This is called, for example, cross-age recognition. So on the left, we have the pairs from that standard benchmark, which we can see it's pretty similar pictures of people in like different contexts and so on, but still they're all pretty similar. But then on this new version of the data set, we have these people decades apart. So this is a much harder problem where we want to generalize the stacks to, okay, can we take a teenage picture of this person and then recognize them 20 years later or something like this? So this is one of the new areas of research here. We have also what's called cross-pose detection. We still generalize pretty well in terms of recognition across different poses once we have several pictures of that person in different angles. But let's say we only have a single picture from you from a certain angle. Can we now recognize you in all sorts of angles from like that single picture? So this is a new area of research. We have things, let's say, like called cross makeup. So for example, in the pictures here, they're all pictures of the same person. And this is a challenge even for us humans, but especially so for models, since they rely on a lot of factors that might have changed in contexts like this. So the model should be able to recognize this as the same person in all pictures.
Is this all machine learning? Or do you explicitly tell what aging elements to expect or what makeup is looking like?
Sorry?
Do you explicitly tell the model what makeup is looking like or what aging is looking like?
So in the original models, no, you're just feeding the image and the model is learning that by itself. But as people are tackling those sorts of problems, there are different approaches. Some people try to tackle this without explicitly saying what makeup is, by, for example, giving examples of people across different sorts of makeup, or trying to pre-process the image such that the makeup is less evident. And then some other direction of research is based on trying to do some manipulations on the image such that the makeup is less intense or something like this. Or even in the case of age, I think is more explicit. There's some interesting research where people try to apply some neural network that can change the age of the picture into a common age, and from that try to make the recognition. So this is called, again, generative adversarial network. You feed it, let's say, your teenage picture and an old person picture, and it's going to try to age that into, let's say, 40 years old or something like this, and then use that image for your final prediction. So there are several areas of research in those areas here. And beyond those cross-factors research, there are different areas that are tangentially related to recognition that people are looking at. First one is security. There are several different ways you can try to break a system like this. The first one is having a real face go undetected or go misclassified. You might have adversarial users that want that, let's say, in a security system. You could have the opposite, someone having a fake face, let's say a printout or a paper being recognized as a way to fool, let's say, a biometric system and so on. And also, there's a lot of concerns in terms of privacy. A lot of machine learning models retain a lot of the data that they use to train inside themselves. So people are looking into how can you prevent the models from leaking that sort of information or leaking the different classes you have or other things like that you might have. So here's one example. This is what they call a facial recognition proof makeup. Most of the commercial facial recognition systems don't see a face in this picture. This is something that's pretty obvious to the humans. There's still a face here, but we can see the models are still pretty sensitive to things it hasn't seen in the past. So the models aren't generalizing too well to new scenarios, especially for things like this it has never seen before. So there's a lot of research into how can we make those models more robust, like a real person would actually do in terms of looking at a face and so on. There's a lot of work into combining facial recognition of biometrics and other sorts of data. So multimodal data basically means combining multiple sources of data. And this can help you deal with situations, for example, how do you do facial recognitions when you have identical twins or when someone has let's say, plastic surgery and changes their face a lot, and so on. So again, here's another example. This is a person who went through facial surgery, plastic surgery, and again, most commercial facial recognition systems don't see this person as the same person in both pictures. So how can you start dealing with situations like this? In cases like this, then, we can start looking at other biometric data, for example, your fingerprints, your handprints, and so on. We can combine multiple types of sensors, so instead of looking just at a picture, we can look at a 3D scan, similar to what your iPhone is now doing with Face ID. It's not only taking your picture, but it has a pretty granular 3D scan of your face. It's also, people are also looking to combining multiple viewpoints or multiple pictures from a video and so on, and using that to have a better prediction about whatever you're looking at. So again, like I mentioned, this is an example of Face ID. It's not only looking at the picture of your face, but it has a laser sensor that's creating a coarse 3D scan of your face and using that to do the facial recognition here. And then finally, there's a lot of research in terms of privacy. Like I mentioned, if you're working with embeddings and so on, those can contain information about gender and age and race and so on. And a lot of that information can later on be leaked. So how can you potentially extract that information without retaining that sort of data, or without actually considering that sort of information for whatever task you're working with, and so on. So people are looking at ways to make this a more private approach of dealing with facial recognition. And then a secondary research here, it's called homomorphic encryption, which is the idea of how can you make predictions without having the person actually look at your picture. So the idea here is that, let's say you have a phone, you can take a picture with your phone encrypts the picture, sends that to, let's say, a cloud server. The server can make its prediction on the encrypted version itself. It can't actually see what's there, but it can make the prediction. The prediction it makes, actually, it's also encrypted, so it doesn't know what it predicted on and what it predicted, and it sends back this encrypted prediction to you, and then you can unencrypt it and have that yourself, but the cloud server has no idea what it basically did. So this is a new area of research that can greatly improve the privacy on a lot of the tasks like facial recognition and so on. And like I mentioned, detection and recognition are the main tasks in face processing, but there are a number of other interesting areas that people are looking at. So I briefly touch upon 2D alignment, but people are also doing 3D alignment. So can you estimate the direction and position of the face in a 3D space from a 2D picture? Another one is estimating facial landmarks. So in this case, you want to figure out where all those key points in the faces are for, let's say, your eyes, your nose, your eyebrows, and so on, and use that information for whatever task you want to do. There's a lot of work in terms of classification. For example, can you classify emotions or age and so on from your pictures? And then finally, there's also 3D reconstruction. Basically, you start with a picture of a person, and just from a single picture or a few pictures, you want to create this 3D model of the person. So this was to give you some intuition about the theory of what people are working on and how people are tackling those problems. So now I wanted to shift the focus towards the practical side of things and see how people can actually use those principles to build interesting products and so on. So first, in terms of like rapid prototyping, there are a number of tools out there that allow you to work on those different tasks, and there is usually a trade-off between the simplicity of using those tools, both in terms of the implementation and in terms of the hardware resources you're going to need and the accuracy you're going to get. So there are a lot of tools where you can quickly deploy that with like a few lines of code on your laptop. You don't need any GPUs or any sort of hardware like that, and it gets pretty good performance on standard cases. But then once you want to generalize to all sorts of angles and so on, you might need a better model to tackle something like this. But it's often useful to start with one of those simpler models, prove your concept, and then start going up the scale of complexity in terms of like what models you're going to use and so on. And I think it's also important to note that there are a lot of APIs that can do most of those face processing tasks very quickly and very cheaply. So it's often cheaper to do something like this and actually deploy your own GPUs and have very complex infrastructure. Just for reference, a lot of those cloud providers are able to recognize or do all sorts of tasks and faces for 1,000 faces for less than $1 and or something like that. And the advantage of doing this compared to using a simple model, like simple open source model, is that by doing this, you can usually get close to state-of-the-art performance. So they're deploying some of the best models out there and doing this in a cost-efficient way for you. So just for reference, for example, what you can do in Azure, with a simple API call, you can detect the faces in your picture. For all those faces, it's going to classify dozens of properties from gender, age, emotion, a bunch of physical characteristics, and so on. It's going to estimate all those landmarks I mentioned. It's going to estimate the pose in the 3D space. And then it can also do recognition for you. So basically, most of the tasks I mentioned in a single or two API calls, it's able to do all that very quickly and very cheaply. So often if you're creating a prototype, this is often a good way to tackle it first. Another interesting way of tackling prototypes, especially if you're doing something that's not as standard as those services are trying to tackle, is by leveraging the embeddings you can extract from those models. So like I mentioned, those embeddings are used for the open set recognition problems, but they start to store some underlying information about the faces in those vectors. And then you can use those vectors to train whatever other task you want. So let's say we wanted to train a model where you want to detect if the person is wearing glasses or not. We can extract the embeddings from the faces. And then even if you have a small data set, you can use those embeddings then to train your model. And it's a lot easier to train from those embeddings than having a raw picture. So you can have a lot fewer samples, train a lot faster, and so on. And just as an example here, let's say we wanted to create Facebook photos. I briefly mentioned this before. The strategy here is that we could detect all the faces from your friends, from their profile pictures, from the pictures they've tagged before, compute the embeddings from those pictures, and then whenever you upload a new picture, you can compare the embedding from that new picture to all the embeddings that you know. And then you can take the closest one or the average one from your friends and so on, or something like this, and make the predictions. So if we wanted to build a prototype of this, using one of the libraries I mentioned, we can, in 2 lines of code, basically load the picture, this is in Python, and then detect all the faces there. And then once we have the faces, again, with a single line of code, we can extract all the embeddings for those faces. And once we have this embedding, if we simply compare the distance between the vectors without doing anything fancy, the simple L2 distance from any of the machine learning libraries, and apply it to different sorts of pictures, we can actually get pretty good performance. So we see here, we have pictures that have different angles, different sorts of lighting, and the people aren't too far away from each other, so both males, both the same ethnicity, and we still get the same, a good accuracy here. So it's giving you the lowest distance to the same person in all the cases here. So you can see that even in basically 3 lines of code, we could create something similar to a prototype of Facebook photos. Another interesting way to do something like that is by leveraging the facial landmarks. So we can quickly extract, using pre-trained models, again, where the mouth, the eyes, and so on are, and use that information to work on an interesting task. So again, with a single line of code, using a library like this, we can extract all the landmarks for the eyes, the lips, the eyebrows, and so on. This is the picture I showed you before. Basically, this is plotting all the points that's extracted. And then we can use something like this to create something like Snapchat filters. So here, whenever there's a new picture, we can detect all those landmarks where all the facial features are. And then based on those points, we can add new objects to the picture, we can deform the image, we can change the colors, and so on. So here's an example. Here, we're going to draw a bunch of polygons on top of the faces. So once we've extracted those key points, we're going to draw a couple polygons on the lips and around the eyes. And by doing this, we can, in about 10 lines of code, create a digital makeup system. So in this case, we start with the picture on the left. We detect all the facial features for that face. And then on top of the lips, we're drawing a semi-transparent red polygon. And around the eyes, again, the same for a black polygon. And it's a pretty coarse makeup system, but we can see that in just a couple lines of code, we can do something that works pretty well. And if you want to scale then, you can create something that places things on the image. You can deform the image to have all sorts of filters that Snapchat is doing. And then finally, once you've determined what you want to do, and you want to scale this, then there are a number of concerns you might want to have to help you take this to the next level. So the first one is in terms of the biases of your data set. So a lot of people, for example, even from my experience, are collecting data from their coworkers or in your local area, your neighborhood, and so on. And this data set is going to be pretty biased. So if you want to do recognition or some other task using this sort of data, you need to be mindful of the diversity in terms of like the